Thanks, everyone, for coming to this talk. It's impressive, the amount of people that seem to be interested in functional programming in Kotlin. So how many of you are functional programmers or practice functional programming in one capacity or another? Right on. OK, so how many have heard of Lrrow before? Cool. Very good. So in this talk, what I'm going to do is I'm going to give you like a quick introduction to how Lrrow came to be what it is today. And then we're going to do a very simple function refactoring, where we're going to take a function that is impure and side-effecting all the way to purely functional with some techniques that are possible today in Kotlin thanks to Lrrow. So about myself, I'm Raúl. I'm a CTO at 47 Degrees. We're a functional programming consultancy. And we are involved in the Scala, Kotlin, and Swift communities. And I myself, I do a lot of Scala and also a lot of Kotlin, so I'm kind of in between both languages. And Lrrow started as a learning exercise. This is a Slack in the Spanish community where most people from the Android community in Spain hang out, and then they discuss Kotlin, FP, and other tech-related things. And we all started thinking, OK, there was a lot of people that were interested in functional programming. And I had some experience with Scala and other languages doing that. So I kind of wanted them to get an impression of what that would look like in their language. So we started encoding super basic data types like option or try or either just for fun and see what that would look like in Kotlin. Months later, and many people were interested in the topic, there was enough data types and content encoded in the library that category was born. This was before Lrrow. It was called category. And at some point, we decided that we didn't want the same thing that happened in the Scala community, where we have two functional programming libraries, cat and ScalaZ, to happen in the same in the Kotlin community, because that's really disruptive, especially when you come into a project and then there's some infrastructure that you need to encode in one thing, but they're using a different one. So there's subtle differences, and we wanted that to be just a fresh start for Kotlin developers and people interested in functional programming. Have a single place where we can go and look at a library that provides all the functionality that we need. So we talked to Mario, which was the author of Functionality, who knows Functionality from before? OK. So Functionality was a functional programming library with different scope to Lrrow. It was more a lightweight function-related composition and syntax. And category included all the type classes and abstractions that you find in other languages, such as functor, monad, and all those crazy words, right? So what is today Lrrow? Lrrow has a bunch of different utilities. We're not going to cover everything today, of course, because there's way too many things to cover. But we're just going to briefly explain what it's included in the library, and then we're going to go into some coding. So we have utilities for error handling, for computation, for folding, combining, and all of these are called type classes. And the ability that type classes have, which we're going to see in a second what they look like, is that they can abstract away behaviors without specifically talking about a particular data type. So for example, if you wanted to compute, you don't need to speak about Kotlin coroutines or observables from RX2 or flags from Reactor. You can just use the monad type class, because that means sequential computation. And then, using these type classes, we'll see what the properties that our program will gain. Besides type classes, we have tons of data types. So many of you may have already used a few of them, like either, try. OK, so most people start with those, and that's fine. Lrrow is modular. You can pick and choose whatever you're interested in. And to show you what it feels like programming in a purely functional type style in Kotlin, we're going to build a very simple library that is composed exclusively of one function. This library, what it's going to do basically is go to GitHub, fetch some gist information for a given username. And us as library authors, we want these properties in our library. We want first do the actual functional requirement, which is go and get the gist from GitHub. But we also, doing that, we're going to expose an immutable model, which is going to be the gist. And we want our users to be able to use that model in a very same way. meaning no boilerplate whenever they want to update, deeply nested relationships, and so on. We also want to support non-blocking data types. That means that our library should be able to work the same way, whether our users are using Kotlin coroutines, they're using Reactor Framework, RX2, or IO from Lrrow. And finally, we want the entire description of the program to be entirely pure and that has no side effects or effects are deferred to a single point in our application, which is the final goal of type functional programming. So to get started, the function might look simply like this, right? And this is not complex at all. We get a username as a string. We get back a list of gist. So what does a gist look like? So this is the model we're going to expose to our users. It's a simplified model because the GitHub API has tons more properties, but for the purpose of this talk, those are not that important. But we can see here a couple of things. One of them is that the gist itself has a map of files, and it also has an owner. Those two properties are nested properties. So whenever we instantiate this in memory, we're going to have some kind of like graph tree, right, which everything comes from a gist, but there's deeply nested information that we may want to have access to. Instantiating a gist is trivial, and we're using data classes because data classes in Kotlin are immutable, and they have very nice properties such as like automatic implementation of equals and some synthetic methods like copy that is going to allow us to work with that immutable model. When we're using mutability in classes, it's easy because we just call whatever dot equals, and then we mutate the state. But in functional programming, we try to avoid state mutation at all costs. So what does it look like updating right now our model? Using the copy synthetic method that the compiler automatically injects for us in our data classes, we can simply say, OK, I'm going to change the description, so I'm just doing a simple copy. This is a straightforward, and it's not that much boilerplate at all, so it works great. The problem arises when you have deeply nested properties within your model, right? So if you keep copying and copying and copying, you're going to end up with like a nested chain of like functions or not functions, but property invocations that is going to look like that. Imagine if it was, this is like a second level copy only. Imagine if this was like, 10 levels down the property model. It'll get very hairy and difficult to deal with. The reason is because it's immutable. We have to always refer to the property on each copy that we want to pass on to the next one. But Lrrow provides something called optics. Optics is the way in functional programming to update immutable model. Optics have a data type called lens, and lens is nothing but a getter and a setter. So with a lens, you can establish how you get to a given property and how you set its, how you change its value. If you notice here in the variable owner login, down right here, we can see that these lenses are composable. This means that we can take arbitrary lenses from our model, compose them all together to create a nice workflow for some deeply nested property or group of properties that we may want to update right away. But this is still some boilerplate, right? Because you have to write the lenses, and you might not want to maintain that. Lrrow gives you an annotation processor that will automatically generate all of those lenses for you. Those lenses are actually projected into the companion object of the model that you are working with. So when you say gist.owner.login.modify, as in right here, those are all lenses that are composed one after the other. And you can simply just pass the gist, the actual instance that you are modifying, and the function as to what you want to modify. In this case, we're just uppercasing the login name. So great, we have now an immutable model. It allows easy in-memory updates, supports deeply nested relationships, which is great, because otherwise we will have to like call copy and do all that kind of chain nesting if we didn't have something like this. But we still have a ways to go. So the next thing is like we actually need the functional requirement. How do we go to GitHub, and how do we fetch that information? So the naive implementation for that, which is impure and throws exception, might look something like this. You guys can see here that there's a GET request to the network. This request is actually blocking, so that's not something we want in our library. And then you can see also that whenever we get the result back, we might throw an exception, if it's an exception, because the return type that we're using is just a list of gist. Therefore, there's no way to encapsulate inside a list that this is an exception. So the only option we have at this point is to throw it. How can we improve that, right? First, we already covered the functional requirement, but now we have to take care of purity, and we have to take care of supporting all of those different data types that our library wants to support. So usually, when people start with functional programming, the first thing they do is they hear the word functor, monad, and all those things, and that's kind of scary. So let's go with something easier, and they pick up some of the data types that are the most popular, such as either or try. In this case, you can see that either is parametric to throwable, and I could have used try here instead, because a try of A is isomorphic to an either of throwable of A. They represent basically the same information, and they both have branches for the success and failure. We can see here that now we are able to completely remove exception throwing by representing the return type of our function as an either. And whenever we find an exception, we are lifting the exception to the left side of the either. And if we have a positive result, then we lift it to the right side of the either. That's when we say in functional programming that data types such as either are right-biased. That means that all computations that happen through them, like map, flat map, and so on, they operate over the right case. And whenever there is a left case, like in this case an exception, the computation will short circuit, and it will give you back an either of left. So that's a nice way to handle error handling without exceptions, but this is problematic. And the reason this is problematic, and why you might have found that already if you're using either or try, is that either is a synchronous data type. And here we have a synchronous requirement, which is we don't want to block the HTTP GET request. So what do we use in Kotlin whenever we want to do asynchrony? Most people will go towards coroutines. So in this case here, we are now saying, OK, well, this entire computation, I might as well just run it deferred. And that will give us back a defer of either, of throwable, and whatever. So as you can see, the problematic thing here is that as we include the effects we care about in the type signature of our functions, they keep nesting down, and it becomes harder to get to the actual value that we care about. In this case, we care about the list of gist, but handling this function is going to require us to do something like this. We're going to have to, first, we can remove the defer from the equation, and as Ben had mentioned in his talk previously, we can use suspend. So now all of these computations are asynchronous, they are non-blocking, but they still remain problematic because what they get you back is an either or a try or whatever data type you're using to control error handling in Kotlin. So this forces us to inspect the result and ask it, is this a right, is this a left, and then do appropriately with it. But we can do a lot better than this. And if you're using today coroutines and defer and either and all of these data types, there's ways for you to get to the value that you actually care, and that is called monad transformers. So Lrrow provides a bunch of monad transformers. One of them is called either_t, and what either_t does is, for whatever effect you have that encapsulates an either, in this case the effect is deferred from Kotlin coroutines, we're able to flat map all the way down to the actual value that we care. So whenever we are calling here this async computation with either_t, and we bind it, the resulting value on the left side is going to be the list of gist. It's not going to be the either, because if the either was left and it had a throwable, this entire computation would have short-circuited, and then it would have returned the left. This is complex, because you may have other data types besides either, and so you need to include other monad transformers as well. And monad transformers come at a cost in Kotlin, which is inference is not that great, so you have to specially type some of the cases when you use monad transformers. But there's an even better way to do all of this where you don't have to worry about coroutines or you don't have to worry about any of this. And I'm going to show you guys that in a second. So we have a function that represents our library that has a nice model that is immutable. You can deeply nest it, update it. We have control effect. We're exposing already some of the data types that we wanted, which is defer. We're not throwing exceptions. And we have pure functions that always return whatever they have to in the return type. But now we have to support observable. We have to support flags. And we have to support I/O. So if you don't use Lrrow or you don't use any kind of technique like the one I'm going to show you now, otherwise you will have to probably implement different versions of the same function for each one of these different data types, or provide conversions that move from one data type to another manually. But Lrrow brings you the power to define programs in terms of abstractions and then leave the runtime forgotten, so you don't care about whether it runs in coroutines, or it runs in RX2, or it runs any of the popular frameworks that you use. We don't need concrete data types, and for that we're going to use type classes and polymorphism. And that's what the real power of Lrrow as a library. Here we're going to use a concept called higher kinds. Who here have heard of higher kinds or knows what it is? OK. So higher kinded types, for those of you that don't know what that is the ability to refer to a container that has a hole on it generically, without actually talking about what kind of container that is. So if you think about types that you use today, like list of A, if I could refer to list as a container with a hole, I could say that list is in a higher kind position. And the same with defer or I/O or observable. So this is what a type class looks like. A type class is nothing but a plain interface that has a type parameter, which is targeting a given data type. In this particular case, we don't know what the data type is. So we use kind f of A to say, this function returns something contained, and the contained actual model is a list of gist. But we're not saying this is a defer value. We're not saying this is an observable. How does higher kinds work in Lrrow? So unfortunately, the Kotlin compiler does not have support for higher kinds yet. And we emulate that in Lrrow. So how do we do that? So a way to emulate higher kinded types is through, there's a paper by Jeremy Jalop and Leo White, which basically showed that for any type system that is monomorphic, like in the case of Kotlin, where types are applied and there's no notions of higher kinded types, you can use generics. And if you use a type generic that has two holes, you can use the first hole to represent the actual container, and the second one, the value that is contained within. This is just boilerplate. Lrrow generates this for you automatically, but you can also write it yourself. And the technique is basically, for every data type that can be higher kinded, you need to extend this kind for option of A. In this case, the data type is option, and that's all it takes. With that, you can represent higher kinded values in Kotlin. And then finally, the Kotlin compiler at this point doesn't know yet that option of A or Lrrow kind for option of A is the same type as option, even though they extend each other. So you have to downcast it. But Lrrow does that for you. So how can we implement a computation in the context of f? We don't know yet what that f is. It might be a list. It might be a defer value. It might be RX2. But we can represent the potential placeholder with kind at this moment. So an example of a type class, to give you a little more context. So who knows what a functor is or has heard of functor before? Okay. Who's mapped over a list? Okay, you know what a functor is then. At least in practice, right? So a functor, the only thing it does is like you provide a function, and for any container, it allows you to map the inner context of the container to a new value. So in this case, we have a function that goes from A to B. See, if the container contains an A, we end up with a container of f of B, because we transform the value. And type classes, and in this kind of polymorphism, is not only for abstractions. Like you can say live down there can be actually concretely implemented. So what do we do once we define a type class that defines this kind of behavior? We can provide then instances for the different data types that we want to support. Lrrow provides this automatically for you for all the frameworks that we're mentioning here. So you don't have to code any of this stuff yourself. This is already built in the library. So what does it look like to, say, mapping over a defer value? Pues just invoking map over it. The same for the I/O value. We're just delegating in this case because the actual data types has the operation called map. And you've done this before with many other data types. You've done it with maybe try, either, or list, or any of the actual collections in the Kotlin standard library. So besides functor, Lrrow is going to come with like tons of other type classes. We're not going to go into explaining what they do here, but I recommend you that if you've done something like, who's done RX2 development before with observables? Okay, so there's tons of combinators in observable that you already know, like map, flat map, concat map, and so on. All of those combinators are not specific to streaming, and they're not specific to observables. They're not specific to list or to anything in particular. They have nothing to do with the data types. The data types just support that kind of behavior. Those combinators exist as abstractions, and they can be modeled for all containers in terms of type classes. And they are grouped in the type classes that you see here. If you wanted to lift errors, like exceptions, you can use applicative error. If you wanted to compute sequentially and still short circuit on error, you can use monad error. If you wanted to compute sequentially, you can use monad, and so on. So you can make your programs depend on these abstractions instead of the actual concretions that frameworks give you. So given that some data types are able to support some of the type classes and some others are not able to support. Like, there is no way to represent an exception inside a list where the list has other values, because list has no combination or way to store that kind of information. So you can see here that in the case of list, you cannot provide an instance for monad error, so you cannot raise errors, you cannot do a side effect suspension with monad defer, and you cannot do asynchrony. But there is other data types that do support those kind of behaviors. So if we're talking about something like either, because we have a left side, then we can lift throwables and other exceptions to the left side. And the same with other data types. And now if we have async data types, like Kotlin coroutines, which we are able to lazily start if we want to, in that case, we can do things like effect suspension. So for example, defer from Kotlin coroutines is able to support all of the different type classes that you use when you encode an application in these kinds of abstractions. So we can go back to our function, and then we can go and forget completely altogether that this was implemented with Kotlin coroutines. And for that, we're going to use the async type class. The async type class gives us a single combinator called async that sends us back a callback that we can invoke whenever a third-party async library finishes its computation. So imagine, in this case, we're using an HTTP client to get the gist, but this could have been retrofit returning a result and a potential error. So this allows us to integrate with third-party frameworks that are not written in a functional style. In this case here, we're saying, OK, this is going to be async. We're going to do an HTTP get, and this response string combinator inside HTTP get takes a callback. So this actually does not block. Once the callback completes, we can successfully invoke the async callback that we receive from our type class, and then lift the results to the left or the right if there's an error, if it's an exception. As you may have noticed in the type signature of this function, we no longer are parametric to or using defer or Kotlin coroutines. We're saying this is a container. We don't know what it is, and it may contain inside a list of gist. And finally, as the same way we have this simple API function that is in one of our services that we're exposing in our library, we may have other things going on, right? Like a logger or things that are working together. So the same style and technique you follow with the definition of all your services and classes. And then if you don't if you're not using a dependency injection framework, which you can use Dagger or others, you can also manually construct the module yourself, like I'm doing here, because the boilerplate is minimal. So here, just saying my async instance is going to be an async of f. My logger is going to be this class that I am using for logging. My data source is going to be this thing, and so on, right? So you can have multiple things, combine them. Type classes don't enforce inheritance. So think about them as in, you don't need to implement comparable or extend comparable in a data type for it to be comparable. In the same way, you have a comparator interface in Java, which is outside of the data type. So type classes are all about horizontal composition. They don't enforce inheritance, and they nicely compose with each other. So once we have this module, which we are just basically exposing our function in the API object, we can then make it concrete to what we want to achieve. So we wanted to support Kotlin coroutines. So we can simply create a runtime for Kotlin coroutines by using the async instance that is declared for Kotlin coroutines. Now, when we call a public gist for user, we can see here that the effect is controlled. The coroutine hasn't started yet, but still we are able to run our entire code with the runtime of Kotlin coroutines, delegating everything we're doing to it. But we've never actually used any of the combinators in our implementation. It's just part of the type classes instances that Lrrow provides already. And the same way we're doing for Kotlin coroutines, we can do for Reactor frameworks. So if you're using a Spring Boot or any backend framework, your programs that you're writing for one platform, you can port them to the other and then just run them in a different runtime. So here we are executing this method, and it's giving us back a value encapsulated inside flags, the data type that uses Reactor. Same for I/O. If you're using Lrrow directly and you're not using any of these concurrency frameworks or any of these integrations, you can use the I/O data type that has the full power of all of the type classes in Lrrow and can serve as runtime for async computation, parallelism, and all the kind of stuff you can imagine from concurrency. And the same for observable. So now we have the same library. We have 3 different artifacts that depend on 3 different runtimes, but our code base is entirely polymorphic and abstracted away from the actual runtime implementation. So now we have a library that it's immutable. We can fetch the gist. It's async non-blocking. We support all of these different data types. We don't throw an exception, and it's entirely pure. That means that we can take all of those functions in isolations and test them without the need for mocks or spies or anything, because we can just take the function, run it to a runtime, and then inspect the value. We can also create our own custom test runtimes by implementing the Lrrow type classes if we want to test without asynchrony or if we don't want to use any kind of machinery. So the functional requirement was met. We took care of the immutable model and all of the deep nesting with optics and lenses. We're using polymorphism to abstract away completely the runtime to which we're running our programs to. And we're using the effects library from Lrrow, and that's where the async type class comes from, which automatically takes care of exception handling and managing that kind of asynchronous computations. Lrrow is modular. If you think this polymorphism thing is a crazy thing to do, you don't have to do it. You can pick and choose what you like. So if you just are interested in either, try, and all of those simpler data types, you can just use the core packages. We also have type classes packages if you want to run your own instances. And the type classes packages come with laws. So for every type class that you implement, say you have a new data type, like you're saying, I'm implementing async or effect for completable future. Then you can run the Lrrow laws over the data type. And with property testing, it will run 1,000 tests for each combinator, making sure that your data type holds to the laws of that particular type class. But we want to make this style of programming better. And the Lrrow team and people from 47 Degrees and other people interested in pushing functional programming and type functional programming in Kotlin have submitted this key proposal to change some changes in the language to include support for type classes natively. If you are interested in what I'm showing you and you want to see even less boilerplate and bring compile time dependency injection to the Kotlin language, you can comment here, vote for it. If you don't like what I said, also come and say why you don't like it. Let's discuss it, because this is an open proposal for the entire community. And we're lucky enough, too, that Tomás Ruiz López, who works for 47 Degrees, has been kind enough to do a huge crunch before this conference to get a proof of concept that implements everything proposed in KEEP 87. So you can go today to this URL, and you can download a version of the Kotlin compiler that you can just run a Gradle task and then get a version of IntelliJ and feel what type classes feel like with everything working, syntax, and all that is proposed. I'm going to give you a quick peek, code-wise, what this might look like in terms of changes. I don't promise this is going to get accepted, and I don't promise the syntax you see is going to be the final, but this is what we have so far. So a type class is nothing but an interface, and it's an interface that you can already compile with regular Kotlin today. And this means that existing interfaces, such as comparator and other ones that are modeled in the same way with one type argument, they will work as type classes once this gets approved, if it does. So in Kotlin, here, I'm showing you this is not specifically only to functional programming. This is actually good for OOP programming as well, because you get compile time verified dependency injection. And that's huge. That's huge because you no longer have to use runtime frameworks for dependency injection or resort to like code generation. How does this work? Here we are taking the same spirit as Swift, where we're defining a family of extensions for a given type. You can do extensions today in Kotlin, extension functions, but you have to individually import them. What you lack today is the ability to refer to that list of extension functions as a single unit that you can depend on for an entire scope. And this is what type classes is going to give you. Here we're declaring that the repository that we defined previously, it's targeting a given user. And the implementation, we don't care about it. The point here is the ergonomics and how this is going to feel in terms of programming. So we can define, if we had a save function that is parametric to A, and we have a static cache function, we can do the same for a given user. So with this simple declaration and this new keyword called extension, the compiler is going to be able to know that when you require a repository for a given user, this is the one that is going to get injected for you automatically. So how does this work? The approach in Kotlin that we are following is similar to how type classes work in Haskell. They are coherent. They are coherent in the sense that either the type class author or the data type author is responsible to provide the instance of each other, and they do so by including that instance, this class, in one of the sub-packages of the actual type class. That means that the compiler is going to be able to find user repository in the sub-packages of repository, but also in the sub-packages of users. So this gives you the flexibility as a library author to define type classes, provide instances for the data types that you care to support at that moment, but also for new authors of new data types to provide instances for your type class while preserving coherence. So once we have this definition and the compiler is able to find it, we can then write functions that are polymorphic and that depend on the type class's scope to perform the work they do. In this case, we are writing a persist cache function that uses both functions in the type class to first retrieve the cache, which is a list of whatever, and then secondly, save the cache. We can see here that if we invoke persist cache with user, since the type class instance for a user is in scope, the compiler is able to compile and run this. And it injects automatically the actual instance on the parameter here called R. What this also means is that if you don't want to use this implicit discovery to inject the arguments, you can manually pass them as well. So you have the flexibility to call this from Java code or elsewhere, and then just provide the instance manually. Things will work the same way. Now, what happens if the compiler, if you're trying to run and execute this function for a data type that does not provide an instance for repository, in this case, invoice? The compiler will fail. So the compiler is able to give you an error message telling you what you're missing, where you can place it, and basically is verifying your dependency graph at compile time. The compiler is also able to distinguish strategies for injection. So in this particular case, we're using an object. So the injection is going to be a singleton value. If this was defined as a val, it will also be a singleton value. If it was defined as a function, the compiler will generate a default value in the argument where it will instantiate the function. And if it was defined as a class, it will do the same way. Additionally, type classes may depend on other type classes. So you have inductive resolution to find the instances, like the case for, say, the monoid of option needs the monoid of A, then therefore the compiler is able to recursively find all of the dependencies that you have in your graph before you can run your code and give you a compile time error. This is huge for safety. So we plan to submit this proposal finally once we receive your feedback. So if you have questions, doubts, or you dislike it or whatever, come to the PR for KEEP 87, voice out your opinion. And we also want to work closely with the JetBrains compiler team to propose something that actually makes sense for the future of Kotlin. And that's what I said too, like, the syntax that I show you may change, but this is the concept of type classes, and this is how it works, not just in Kotlin, but in most languages that support it, such as Haskell, Scala, and so on. And finally, Lrrow is inspiring a bunch of libraries that I want to acknowledge here. We're heavily based on the previous work that Katz and Scala set did for the Scala community. And we also try to be more of like a solution for all functional in Kotlin. So we not only include the basic type classes and data types, but we also give you a lot of utilities for dealing with immutable data, such as optics, which come from Monocle, and so on. Join us. We are an inclusive community. We are not the, don't be afraid, this is not an elitist group of people that talk about functor monads and kind of like have fun with that. It's more of a, we want to bring type functional programming to Kotlin because we think these ideas are worth spreading. And we want you to be part of it regardless of your level. So if you have no idea what a monad is, you have no idea what a pure function is, you're still welcome, and we have work for you to do. So we have tons of like beginner-friendly issues that we need to improve the state of Lrrow in this ecosystem. And we provide one-on-one mentoring in the Kotlin Slack and also on Gitter and other channels. So please come and say hi. You'll be welcome for sure. If you want to learn more about this kind of a style, Jorge Castillo and I, we're running a workshop in Lambda World. Lambda World is a functional programming conference in the south of Spain that is happening at the end of October. And we're going to show you how to build backends with Lrrow on top of Ktor. So this is a great opportunity to dig down in pure functional programming on the server side as well. And finally, that's all I have. And I want to say thank you to 47 Degrees for the help and everything they're doing for the functional programming community, to the Kotlin community for being here and listening to this talk, and to Lambda World for inviting us well for the workshop. Thank you.